During this presentation, we will discuss parallel lines, medians, transversals, similarities, and proportionality. This presentation is done in conjunction with Dr. Akbar's geometry class, spring 2017. Presenters are Mr. Ricardo Martinez, Mr. Charles Hawkins, and Mr. Ovis Khan.
Parallel lines are two lines that are always the same distance apart and never touch. In order for two lines to be parallel, they must be drawn in the same plane, a perfectly flat surface like a wall or sheet of paper. Parallel lines are useful in understanding the relationship between paths or objects and sides of various shapes. For example, a square, rectangles, and parallel lines are sides across from each other that are parallel. In formulas, parallel lines are indicated with pair of vertical pipes between the lines named like this. On triangle ABC, the line UV is parallel to line BC. Each line has many parallels. Any line that has the same slope as the original will never intersect with it. Lines that will never cross, even if extended forever, are parallel. In the example number 1, from point A to point B is one line. From point C to point D is another line. So the line AB is parallel to line CD. On example number 2, there is two horizontal lines that it will go forever and will never intersect. Those are parallel lines. Lemma can be considered a minor result, and its purpose is to help prove a theorem or a step in the direction of proof. Let U and B be the points on sides AB and AC of the triangular ABC. Then UB is parallel to BC if and only if AU is divided by AB is equal to AB divided by AC. A median of the triangular is a segment that joins a vertex of the triangular to a midpoint of the opposite side. On example number 1, the triangular ABC, we got one median from the vertex A to the midpoint D, which the opposite side is B to C. On example number 2, we have two medians where the vertex B goes to the midpoint E and the opposite side of the E is A to C. And the second median, the vertex C, where it goes to F, that is the midpoint of the opposite side from A to B. And the last example is so special that we got three medians that intersect at one point. So the first median goes from the vertex A to D, which the midpoint of D is the opposite side from B to C. The second median goes from the vertex B to E, that E is the midpoint of the opposite side from A to C. And the last median goes from the vertex C to F, that is the midpoint from the opposite side A to B.
During this section, we will discuss similarity. Two geometric figures are similar if they have the same shape. Notice that we have many different pentagons of different sizes, but their shapes are the same, hence similarity. During this section, we will discuss the similarities amongst triangles. The shape of a triangle is determined by its angles. Two triangles are similar if the three angles of one triangle are equal to the three angles of the other triangles. Hence, we see triangle ABC is similar to triangle XYZ. For example, if we are given triangle ABC and triangle XYZ, and we know that angle A is equal to angle X, and angle B is equal to angle Y, and angle C is equal to angle Z, then the two triangles are similar. We denote this as triangle ABC is similar to triangle XYZ. If two triangles of one triangle are equal to the two angles of another triangle, then we automatically have equality of the third pair. What I'm saying is, if you know that the two angles of one triangle is equal to the two triangles of another triangle, then it is automatic that the third angle in the first triangle is equal to the third angle in the second triangle. Once again, two geometric figures are similar if they have the same shape. Basically, it is the mini-me of the larger triangle. We'll now discuss Theorem 1.27 from Geometry for College Students by I. Martin Isaacs. In his text, we talk about Theorem 1.27 given that triangle ABC and triangle XYZ. We're going to suppose that angle A equals angle X and angle B equals angle Y. Then we know that angle C equals angle Z. And so, therefore, triangle ABC is similar to triangle XYZ. Proof. Since the sum of the triangles is equal to 180, we have angle C equals 180 degrees minus angle A plus angle B equals 180 degrees minus angle X plus angle Y is equal to Z as required. We will now discuss proportionality. In Theorem 1.28 from the text, Geometry for College Students by I. Martin Isaacs, we say that if triangle ABC is similar to triangle XYZ, then the lengths of the corresponding sides of these two angles are proportional.
When you cross two parallel lines with the third line is called a transversal. There are 8 different angles in a transversal. Interior angles are the angles on the inside of the two parallel lines. Exterior angles are the angles on the outside of the two parallel lines. Vertical angles are the angles that are on the opposite sides of the intersection between the transversal and each parallel line. These angles have the same measurement and are equal. One good way to remember this is the X shape they make. We like to call this the X factor in Dr. Akbar's class. It's fun and a little catchy. The angles that are formed on opposite sides of the transversal and inside the two lines are alternate interior angles. These two angles are also equal in length. Just like with vertical line angles, a good way to remember this is the Z shape they make. You can probably guess what we call this. Yes, the Z factor. Alternate exterior angles are similar to their interior counterparts, but instead of being inside the two lines, they're on the outside. These angles are similarly congruent and equal in length. You can use the transversal theorems to prove that angles are congruent or supplementary. Now we are ready for the main proof, problem 1.30. In triangle ABC, draw UV parallel to BC. Show that the intersection of BV and UC lies on the median of triangle ABC from point A. If we first start out by drawing line UC and BC, we can see they cross at a certain point which we are hoping will lie on the median of triangle ABC from point A. Let P be the point at which BV and UC meet and draw a line connecting A to BC where the line crosses P. We'll denote
the points where the line crosses UV and BC as D and E, respectively. Since there are several lines to work with, we will denote the length UD, DV, BE, EC, DP, and PE by R, S, M, N, X, and Y, like in the image below. To prove the solution to this problem is true, we must show that E is the midpoint of AC, or say that M is equal to N. Since we know that UV is parallel to BC, and we learned from earlier that by lemma 1.29 that angle AUD is equal to angle ABE, and angle ADU is equal to angle AEB. And by the angle criteria from earlier, triangle AUD is equal to the triangle ABE. For proportionality, R over M is equal to AD over AE, and similarly, S over N is equal to AD over AE, which means that RM is equal to S over N, or N over M is equal to S over R. Now, if we look closer and look at triangles DUP and ECP, since UD is parallel to EC, we can tell by transversals that angle DUP is equal to angle PCE and angle UDP is equal to angle CEP by alternate interior angles. Therefore, triangles DUP and triangle ECP are similar, which make R over N equal X over Y. Similarly, triangle DVP and triangle EBP are similar, and they show that S over M is equal to X over Y, which we can then conclude that R over N equals S over M, or M over N equals S over R. Previously, we showed that N over M equals S over R, so we can infer that M over N equals N over M, which concludes our proof that N equals M, which means E is the midpoint of BC.
At this time, we would like to acknowledge and thank Dr. Akbal and the University of Texas at Dallas for the opportunity to be able to present to you our theorems and knowledge.